Hello, welcome to this video on sampling. In this series of videos, we are going to look at the aspect of sampling continuous time signals and representing them using their discrete time versions, and also try to find out why this problem is interesting and how we can potentially go back from the sampled version to the original continuous time signal. On several occasions, we actually have the need to look at continuous time signals. So let's say you have a signal like this. This could be a speech signal, it could be an access of an image, it could be a temperature measurement. There are several possibilities. The issue with the continuous time signal is that it has a value at every value of t, and representing and storing the value for every value of t in a computer for processing is impossible. But if you look at this particular signal, it seems to have some nice properties about it. Let us say that we record only this value, this value, this value, this value, this value, and this value. It appears that just by recording these values, we are able to just reconstruct the original signal. Of course, we may not be able to represent the original signal with full accuracy, but at least maybe with sufficient accuracy. Is this always possible? Is it a faithful reproduction? Maybe, maybe not. Because in between, what could happen is that something like this could happen. Let us say that in between, a sudden jump happens. If you take samples at this rate, these jumps are going to be completely missed. So there looks to be some bit of a puzzle. So there is some property of the signal which should allow us to say, okay, if this property is satisfied, then you can use these red dots, which are the samples xn, to go back to the full x of t, right? So to study how that is going to be done is the purpose of this sequence of videos. To understand this thing better, we recall the Fourier transform, the continuous time Fourier transform. From signals and systems, you would remember that a continuous time Fourier transform is this particular construction where you can actually break a signal down into its component frequencies. And since it's breaking up into the component frequencies, we call this the analysis formula, while reconstructing the function from its Fourier transform involves using the synthesis equation. One thing you must remember is that the Fourier transform is defined only for square integrable signals, which is, in engineering terms, finite energy signals. Now that seems like a restriction, but this will satisfy many of the signals that we deal with practically. Now, what is the intuition behind the continuous time Fourier transform? Basically, it goes to show that you can either express x of t in the time domain as a set of scaled and shifted impulses. That is, if you know the value of x of t at every t, you can use this convolution with the delta of t minus tau to represent it, or you can also use the frequency notation to reconstruct, to represent the signal. Like if you look over here, you're essentially reconstructing the signal from its frequency components. There is a very important connection between the Fourier transform and the ability for you to go back from x of n to x of t, and this connection is something we will explore. While there are several Fourier transform pairs that you would have studied in signals and systems, I will just do one example over here. I'm going to do the Fourier transform, I'm going to give you the Fourier transform for a particular signal, and that is the rectangular Okay, so let's make this neat. Draw a line. Okay, so if you now look at this rectangular signal, let's move this. Okay, so if you now look at this rectangular signal, let's say that over here we have, okay, I should move to this board. This is minus half hertz and half hertz in hertz, and let's say this is the Fourier transform. If you plug this back into this formula over here, the synthesis formula, you can show that what you will get will be sinc of t, that is sine pi t upon pi t. Now this is interesting. This is interesting because sine pi t by pi t is one of the basic building blocks in our construction of the so-called band limited signals. So why would you call this a band limited signal? The reason is because if you look at this particular structure, its frequency range is between minus half hertz and half hertz, and outside it's 0, which means this is the so-called band limited signal. So now, what is the connection between band limited signal and sincs? Let's take another signal which is band limited. Let's say you have, this is another x of f. Let's say it looks like this. It's some Fourier transform. It's very clear that if you multiply this by a rectangle which has exactly this width, let's say this is minus w to w, you will still get the same thing. Or let us suppose that this signal were not band limited and it had some components here. Those will be removed by multiplying it with this rectangle. But what is multiplying with a rectangle in frequency domain? It is basically convolution with the sinc in the time domain. So this is also the ideal low pass filter in continuous time. And what does it do for us? If you convolve any signal with an appropriate leaf space sinc, you will get the so-called band limited signal. So even if a signal is not band limited, by convolving it with a sinc or by filtering it with the ideal low pass filter, you will end up with a signal which is band limited. Why do we care so much about band limited signals? There is a connection between these and the ability to sample and reconstruct them, and that is something we will see in the next videos. Thank you.